All right, ladies and gentlemen, big finish. We got one more type of reaction. We got two examples for this type of reaction. This is another override coming up. So let's just do our analysis right here. Whoa, that was an undo. My computer doesn't want to go away for Thanksgiving. Okay, here we go. Rx. I beg to differ. Your conclusion initially is SN1. Normally, you would just go ahead and write that in the missing conclusion box. Don't at this time. I'll put it there because this is the process. You say tertiary for your first step. You write SN1 here. You may be erasing it with an override though. 2. New ROH. Well, conclusion is SN1. What's the category? You're giving me its category as a solvent, which is analysis step 3 for ROH. Any category of a nucleophile. Nucleophile, strong, medium, poor. Poor. Neutral oxygen nucleophiles are poor. Polar product solvents also favor SN1. So everything's saying SN1. So why is he saying he's going to change his mind? Anybody want to take a stab at it? There's an override.
Yeah, the sulfur.
Yes, the sulfur. Override. There is a nu in the Rx. And here it is. Sulfur is a nu. It's one of our nucleophiles. And it's also in the molecule that has the leaving group. What's the symbol for leaving group? On this question, what's the symbol for leaving group? It's on the screen right now. Br. Generally, it's a halogen. You could have also said X because it's also on the screen. Yeah, Lg is a good short form too. But you had a question before we move on. Oh, perfect. Okay. So this is what's going to be called an NGP, neighboring group participation. Then NGP is what you're going to put in the box. NGP is what goes in the box. Don't like your box? Make it bigger. There you go. No, I don't like that idea. Stands for neighboring group participation. Neighboring group participation. And these, I have to do the mechanism to figure out the products every time. There's no shortcut for me. I don't know if you got one, but I definitely don't have one. So I'm going to do the whole mechanism, even though you don't get any points for mechanism on part 2. But if you don't do the mechanism, you can't figure out the product. So here's how the neighboring group is participating. That's the first step in the mechanism. I put a lone pair on that sulfur. It does what looks like an SN2, but it's in the same molecule. I can't call it SN2 because there's no 2. There's only one molecule there. But if you want to memorize the mechanism, those arrows are backside attack, leaving group leaves. We called that SN2 before. The arrows are SN2. And you get an intermediate that has a box. Either a box or a triangle. In this specific example, it will be a box. Sulfur, CH2 once, twice. Comes up to a carbon that has a methyl on it. And a new bond right here. And the carbon with the methyl also has an ethyl. Do you agree? And two CH2s, and the sulfur also has a propyl. And when you have sulfur with 3 bonds, just like oxygen with 3 bonds, what are we talking about? A positive. It's called a sulfonium. Samsung or Apple, I don't know. Oh, not sulfonium. Sorry.
Do we have to turn it into a box?
No, it can also, she asked, does it have to turn into a box? And the answer is no. If the leaving group was 1 carbon closer, it would make a triangle. This reaction only works if box is possible or triangle is possible.
So Professor, the CH3 over here was from the back, right?
This CH3 used to be here. Stereo center, it's I don't have to draw the stereo center. I just have to know that if I start with a stereo center that used to be S, not R, therefore S in this case, I'm just going to write the R here. It's not my final product. I don't have to worry about it yet. Okay? Do you agree when you do a backside attack, stereo center flips? That's a fact. Now the question is, your nucleophile, it has a choice of attacking one of the carbons attached to sulfur in the square. And the question is this. It's an interesting question. It's not about picking the carbon that's the better cation. It's not about that. It's about picking the carbon that's easier to get to. The carbon that's less blocked. So here's your 2 choices. I'll put a blue dot on them. You can attack that one and pop open the red bond, or you can attack the least hindered one here and pop open this blue bond. It has to be in the square attached to the sulfur. So I didn't even ask about this carbon. It's too far away. This one won't relieve the square strain. The only reason we're doing this next step is to relieve the square strain.
And we'll do the one that's not
The least hindered one on the bottom. The least hindered one on the bottom. And now sulfur got its lone pair back. Sulfur happy again. This is still not in the box. We're still not finished. We're darn close, but we're not quite finished because we have something with a pKa of -3.
Yeah, we have the OH.
Yeah. So our new bond is here, and it goes up to a CH2, which goes to a C with an ethyl and a methyl and an H. We'll figure out the stereo center in a second. And I gotta make sure there's the CH2, that's a blue dot. Yeah, and that's a plus. And we didn't change, did we do anything with the stereo center in this last step? Was it attacked? No. So whatever it is what it was. No, dude. What it was is R. So neutralize that oxonium and draw the stereo center properly finally. Uh-oh. She thinks I drew something wrong, and she might be right.
I think the C3 and the ethyl should be on
The O attacks a CH2.
no, but you didn't draw on the right carbon.
Oh, is this drawing incorrect? The sulfur that used to be bonded to CH2, CH2, CH3, CH2, CH2, CH3, that part's fine, is now bonded with a new bond to the carbon that has the methyl. New bond in between our 2 CH2s. Here they are. Carbon with a methyl also has an ethyl. I don't think I've seen a mistake.
Oh, you switched like this now.
I didn't do any switches. Yeah, okay. The sulfur has to be on the carbon with the methyl because it attacks the carbon with the methyl. You have it 2 carbons away. There you go.
But, shouldn't it be R in the beginning?
It was not R, therefore it's S. Oh, that is a number 4 group on there. I had in my brain the methyl on a wedge, didn't I? It's okay. We just changed both of them, right? Yeah. I'm always thankful for students that are helping me out. I clicked up there, dude. It will not get rid of that box for me.
It's my fault, I confused you earlier.
No, you did not. Student was apologizing for confusing me earlier. They did not. There we go. So, in review, Stereo Center 1, 2, 3, with the 4 already on a dash, it's straight up right answers are. When you do a backside attack on R, it's S. We just have to make sure we draw it as S and then draw it in the box. So I'm pretty sure H on a wedge. Methyl on a dash does it, right?
Yeah.
So let's copy that. That is a weird wedge. Oh, harsh. And then CH2 once, twice to an O, ET. And where's our sulfur? I didn't finish drawing. This is not the, we're not finished with this thing, yeah? The carbon attached also had CH2 plus the carbon that has an S. There's no H up here. Yeah, I am too, because this is a disaster up here. Let's fix it together. If I can find my pen. O attached to C. O attaches to the C that's the dot here. Do we agree? The C that's the dot there is also bonded to CH2 to the left, which is bonded, I'm up to here now. You see it?
Yeah.
Which is bonded up to here, right?
Yeah.
And there's an ethyl and a methyl and a sulfur. That bond was there before. And now I understand why the heck you were confused, because yeah. If you weren't confused, I'd be surprised. So you attach the O to the CH2. There it is. O bonding to CH2. No longer bonded to S down here. No longer. This bond is no longer. The CH2 is still bonded to CH2 here. There's the CH2. The CH2 is bonded to a carbon that has both a methyl and an ethyl. The C has both a methyl and an ethyl. The carbon with the red bond to sulfur, that red bond did not change. The red bond did not change to sulfur. Sulfur got a lone pair back, so it's neutral. Still has its propyl. We're here. Every time I went back and forth, that was bothering. So that is not what we're drawing, is it? CH2 once, twice, good so far. Up to a C. There's no H in the molecule. That was the giveaway. I knew something funky was going on. Let's just draw it and then work on the stereo center. How's that? And we need to make this thing. S did not change in that last step. Neither should it change in this step. So methyl on a wedge. Ethyl on a dash. And that should be it. Sorry for the confusion. But the important thing though, we got a new override. Yeah. RX has a sulfur in it. It's an NGP. As soon as you see that, cross off your previous conclusion. And secondary, just tell me if I lose anybody here. Haven't lost anybody, right? Yeah, when the solvent appears to be missing, then the nucleophile and solvent are the same species. So the same analysis as above. I should have just written that. No, it wasn't. Tertiary changed to secondary. And based on what you got there, if you haven't done an override, you would write originally SN1, wouldn't you?
Yeah.
That's not going to stay because this new in RX. And you're saying, wait, Dr. Whitaker, phosphorus is not on my list of nucleophiles in chapter 9. And Dr. Whitaker says, wait, young students. Periodic table, Chem 141 says whatever nitrogen does, phosphorus pretty much does the same thing. So if you have a list of nucleophiles with nitrogen on them, you can say the same for nitrogen, phosphorus, sorry. Moderate. And in fact, it doesn't matter what category the nucleophile within the molecule is. It can be strong, medium, poor. If it's in the molecule that has the leaving group, it's NGP. I don't care what kind of nucleophile it is. Got it? And this one's going to make a triangle. You know how I know? Because I'm going to do the mechanism. Backside attack on something that used to be, this one for sure was asked. I'm doing the mechanism underneath. Once again, no points for it, but if I don't do it, I probably won't get any points anyway. Copy the green. Just copy it as you see it, and then worry about the triangle. The triangle's here, isn't it? And now phosphorus has 4 bonds. It's a phosphonium. And the S stereocenter has to be R. I don't have to draw properly yet. You're allowed to attack one of those 2 carbons attached to phosphorus in the triangle. Which one's easier to get to? The one on the left or the one on the right? Here's your 2 dots. Left is more substituted. Right is less substituted. Right here is easier to get to. Primary versus secondary. Yeah. So this is a new deal for us. We haven't done that before. We've always looked at, oh, attack the more substituted position. It spends more time with a plus charge. This is not about that. This is about the nucleophile having easy access to one versus the other. And it's got to do the attack on this position here because it's less hindered. That makes it neutral there, and the ring gets smaller. Yeah, we can go to the final product right now, but I want to do this right here. Here's the green line with the 2 dots. Here's a new bond to nitrogen. Yeah. There was an H on there too, right? It's okay to have an ammonium product. The greens didn't change other than the one attached to phosphorus. So there. And phosphorus is there. And it's bonded over here now. And I got to make sure that thing is R. 1. Phosphorus is 1, 2, 3. That's a dashed H. Wait, it was a dashed H before. Interesting. There still are. There was no kind of chemistry going on there, and there's still a F on the phosphorus. And I think that's just going to get moved up to the box. In the previous one, we had to neutralize an oxonium right here. How come we don't have to do that in our new one? This has to be neutralized. This does not. Weak acid versus strong. So this is our final product. Weak acids are stable products. That's what weak means. Oh, I got extra. So What do you think? Too big. Like it? They are the same thing. Neighboring group participation. Good stuff. That's it. That's it for the day.